Hello, everyone. I present the work titled An Experimental Architecture for Simulating IoT Devices and Evaluating Telemetry, developed by myself, Alana Costa, and Hugo Barros, both from the Federal University of Pará. In Internet of Things applications, network behavior is a critical factor because a sensor reading only has practical value if it reaches the monitoring server on time and intact. Factors such as delays, packet loss, and bandwidth limits directly affect telemetry quality. Therefore, our study shifts the focus. Instead of questioning whether the sensor is measuring correctly, we evaluate how the network affects the delivery, latency, and visualization of these data. To guide this investigation, we defined 3 research questions to discover if Mininet can simulate an IoT network integrated with ThingsBoard, how network degradations affect telemetry, and whether ThingsBoard can adequately monitor these simulated data. Our theoretical foundation divides the IoT architecture into 4 layers: perception, communication, processing, and application. In the communication layer, we use the MQTT protocol, which has different quality of service, or QoS, levels that vary in reliability and computational cost. For processing and application, we adopted ThingsBoard, an open-source platform that receives MQTT data, stores telemetry, and allows the creation of dashboards and alarms through its rule engine. For infrastructure emulation, we use Mininet. Mininet creates virtual topologies, where hosts run real MQTT clients and Python scripts, meaning traffic crosses virtual interfaces just like a real network. Using the TC-netum tool, we introduce controlled faults, such as delays and bandwidth limits, to observe how MQTT traffic, running over TCP, interacts with the protocol's congestion control. Methodologically, we organized everything in a Linux environment using a modular 3-layer architecture. The edge layer composed of Mininet hosts, the emulated network with its virtual switches, and the Fogger cloud layer running ThingsBoard. Our base topology features 5 sensors connected to a central switch, publishing a JSON payload every 2 seconds that contains environmental variables and instrumentation fields, such as sequence numbers and timestamps, which are essential for us to measure losses and delays quantitatively. To evaluate this structure, we executed 5 experimental scenarios. In the normal baseline scenario, we achieved a 99.8% delivery rate with an average delay of only 18 milliseconds, ensuring a near-continuous flow of telemetry. When we introduced 50 milliseconds of artificial delay in the second scenario, the delivery rate remained high at 99.6%, showing that the application remains viable, though less immediate, which could be critical for real-time control systems. The third scenario, with 5% packet loss, yielded the worst delivery rate at 95.0%, causing visible gaps in dashboard time series and potential delays in triggering alarms. When we limited the bandwidth to 1 megabit per second in the fourth scenario, the dominant effect was queuing, pushing the average delay to 118 milliseconds, closely resembling constrained real-world IoT links. Finally, when scaling the network to 20 simultaneous sensors, the high aggregated low-generated contention. Out of 12,000 sent messages, 320 were lost, and the delay rose to 135 milliseconds. Fortunately, we found that ThingsBoard's tools are highly useful for handling this, as the rule engine can transform these telemetry absences into offline device alarms. In conclusion, our work demonstrated that the combination of Mininet and ThingsBoard successfully preserves the full flow of an IoT network, from data generation to visualization. Answering our initial questions, we confirm that delay affects information temporality, losses reduce completeness, bandwidth constraints increase jitter, and network scale introduces strong contention. ThingsBoard proved to be an excellent network thermometer, displaying perfectly continuous graphs in stable situations and reflecting gaps when the infrastructure degrades. For future work, we plan to explore multi-switch topologies, compare the trade-offs of different MQTTQoS levels, and integrate physical sensors like the ESP32 or Raspberry Pi. It is clear, therefore, that this architecture is a reproducible, low-cost solution, highly effective for education and experimentation in IoT networks. Thank you very much for your attention.